Chapter 8 and 9 we're going to combine, and we're going to look at how molecules are created, what kind of bonds there are. And we're going to start out by looking at the basic types of bonds. It turns out there are two basic types of bonds in compounds. We have ionic bonds and we have covalent bonds. Ionic bonds, hopefully you remember from your first year chemistry, are where electrons are transferred from one atom to another, and so we have charged particles that are attracted to each other. In covalent compounds, the electrons are not transferred, but the electrons are shared between the atoms, and the electron pairs between the atoms form the bonds. So what determines what kind of bond forms between two atoms? What we're going to look at are electron affinity and ionization energy. If we have elements that have very low ionization energy, they give up their electrons very easily, they're going to ionize pretty easily. If we have atoms that have very high electron affinities, it's very easy for them to attract electrons, and so they become negative ions very easily. When I combine one of each of those kind, I tend to have an ionic bond. And the amount of energy involved in an ionic bond is determined by Coulomb's law. We took a look at that last chapter. If I have an ionic compound, I tend to have high electron affinities, low ionization energies. And Coulomb's law, if we look at it with numbers, looks like this. So the energy of the bond, which essentially is the lattice energy, equals a constant, and the units for that constant are joules times nanometers. Q is the charge of each ion, and then R is the internuclear distance. So we saw this equation before. We want to take a look and see what this looks like for sodium chloride. We're going to see this. Sodium is a +1, chloride is a -1, so we put those numbers in there. The distance between the sodium and the chloride nuclei is 0.276 nanometers. So we do the math and we get the value for the energy. Because we have a negative sign there, the negative sign in Coulomb's law means we have an attractive force. Is an energy involved in those two ions pulling on each other. So for one sodium chloride particle, we have that negative 8.37 times 10 to the negative 19 joules. In terms of moles of sodium chloride, it turns out it's about 504 kilojoules per 1 mole of sodium chloride. Ions form in the first place because they want to become stable. If an atom is not particularly stable, it will more likely form an ion because ions have an electron arrangement that allows them to be stable. They have electrons in their p and their s orbitals, so they have a full octet. Noble gas configuration is another way of describing this full octet, and it's referred to as a stable octet. 8 electrons, 2 from the s orbital, 6 from the p orbital. So if we take a look at the periodic table, we can pick a few elements and based on the positioning in the periodic table, identify what their likely ion charge is going to be. If we start out with something easy, like sodium. Sodium is in the first column. That means it has 1 s electron, and so it's going to lose that electron and form a sodium +1. We look at something like nitrogen. Nitrogen's in the p block, so it has a full s orbital, has 3 electrons in the p block. Could lose 5 of those electrons, and so lose its outermost shell. It's more likely to gain 3 electrons. If it gains 3 electrons, it'll have an electron configuration like neon, and then it will be happy. It will have a full octet, and that will make it a -3 ion. We take a look at another element. Take a look at aluminum. Aluminum is also a p block element. It only has 1 p electron. To gain 5 electrons is pretty tough. And so it is more likely to lose its 1 p electron and its 2 s electrons, and so that would make it a +3 ion. So for p and s block elements, it's really easy to identify what the charge is. Just a reminder, all metals form only positive ions. Nonmetals can form negative or sometimes positive ions. And the transition metals, being metals, only form positive ions, but they can have multiple positive ion charges. So let's take a look at covalent compounds. Covalent compounds are compounds where the electrons are being shared, and it turns out that there are 3 forces at work to create these bonds. We have the nuclei of each atom that are positively charged. They repel each other, so that would be the PP, or the proton-proton repulsions. We have the electron cloud from the first atom, and we have the electron cloud from the second atom. Both of those are negatively charged, and so we have the two electron clouds repelling each other as well. To balance that out, we have protons from the first atom attracted to electrons from the second atom, protons from the second atom attracted to electrons from the first atom, and so that gives us our proton-electron attractions. And so depending on which of those is the strongest, that determines how strong our covalent bond is. So if we take a look at this diagram, on the left here we have a hydrogen atom, and the dots represent the probable location of the single electron. Not that it has that many electrons, but those are all possible locations for the electron in that atom. Here's the right-hand hydrogen atom. Their electron clouds don't overlap. They're far enough apart, no interaction. And so that's going to be here on our energy chart. They essentially have no energy. I start moving those atoms closer and closer together, and I start getting some interaction between their two electron clouds. The electron clouds initially are going to repel each other. It's starting to get to the point, though, that the nucleus of the left-hand atom is attracted to the electron from the right-hand atom, and the nucleus of the right-hand atom is attracted to the electron from the left-hand atom. So that attraction actually gets stronger as the atom moves closer and closer together. And so what we see at this point is there is some finite distance where the attractive forces between the plus charge of the nucleus, the negative charge of the electron, are the strongest, and that's therefore our hydrogen-hydrogen bond length. Now if we try and keep compressing those hydrogen atoms closer and closer together, what we see happening is the energy goes off the chart, because as the atoms get closer and closer together, we've got this great huge proton repelling another great huge proton, and that really requires a lot of energy to hold them that close together. So the energy goes off the chart. So what we want to do when we're making covalent bonds is we want to reach the lowest energy state for the structure. And so we get the bond length determined by how close we can get the atoms together based on lowest energy. So for hydrogen, the electron exists between the two nuclei, essentially to buffer them and allow the nuclei of each atom to attract both electrons. And so the electrons don't spend a whole lot of time outside of the internuclear region, but they can. And so this gives us a very stable configuration for our hydrogen atom.